For decades, quantum computing existed mostly as an idea discussed by physicists and computer scientists. The promise was enormous. Create machines that use the strange rules of quantum mechanics to perform calculations that would overwhelm conventional computers. Then Google introduced Willow, a new generation of quantum processor designed to push that idea further. Willow contains 105 superconducting qubits. But the significance of the processor is not simply the number printed on the chip. The real challenge is controlling quantum information without allowing environmental noise to destroy it. A classical computer stores information using bits. Each bit can represent a 0 or a 1. Quantum computers work differently. Their basic units, called qubits, can occupy combinations of quantum states and can become entangled with one another. This gives quantum systems an enormous mathematical state space. But there is a catch. Quantum information is extremely fragile. Tiny disturbances from the surrounding environment can introduce errors into a computation. Heat, electromagnetic interference, imperfect control signals, and other sources of noise can disrupt the delicate quantum state. That is why one of the most important problems in quantum computing has never simply been adding more qubits. It has been making those qubits reliable. Google used Willow to investigate this problem through quantum error correction. The basic idea is fascinating. Instead of treating one physical qubit as a perfectly reliable unit, researchers distribute information across multiple physical qubits to create a more robust logical qubit. The goal is to detect and correct errors before they destroy the computation. For years, researchers faced a difficult problem. Adding more physical qubits could also mean adding more opportunities for errors. Willow demonstrated progress toward reversing that relationship. As the error-correcting system became larger, the logical error rate decreased rather than increasing. This is an important milestone because scalable, fault-tolerant quantum computing depends on reaching precisely this kind of regime. Another headline surrounding Willow came from a benchmark known as random circuit sampling. Google reported that Willow completed a particular benchmark calculation in a tiny fraction of the time estimated for a classical supercomputer. The comparison produced an enormous theoretical gap. But that result needs context. Random circuit sampling is not the same as running everyday applications. It is a specialized benchmark designed to expose the computational behavior of quantum processors. It does not mean Willow can suddenly replace conventional supercomputers. It does not mean every calculation will become exponentially faster. And it certainly does not demonstrate that the processor is borrowing computational resources from another universe. That last idea comes from one interpretation of quantum mechanics, the many worlds interpretation. According to that interpretation, quantum evolution does not require the wave function to collapse into a single outcome in the traditional sense. Instead, different possible outcomes can be understood as corresponding to different branches of reality. Some popular explanations of quantum computing take this idea much further, suggesting that quantum computers literally perform calculations across parallel universes. That is a fascinating interpretation, but it is not an established explanation for how quantum computers achieve their computational advantage. Quantum computing can be described using quantum states, amplitudes, interference, and entanglement without requiring evidence that a processor is accessing alternate universes. The practical achievement is already extraordinary. Willow demonstrates how engineers can manipulate fragile quantum systems with increasing precision and use error correction techniques to preserve useful information. That could eventually transform computing. Quantum machines may one day become valuable for simulating molecules, studying advanced materials, investigating complex chemical reactions, and solving certain optimization problems that are extremely difficult for classical systems. But getting there will require much more than impressive benchmark numbers. Researchers need larger systems, better error correction, longer coherence times, improved control, and reliable logical qubits. Willow is therefore better understood not as a computer that has replaced classical computing, but as evidence that one of quantum computing's biggest engineering obstacles may finally be becoming manageable. And that raises a much bigger question. If quantum information can be protected, manipulated, and scaled, how far can this technology ultimately go? The most exciting part of Google's Willow processor may not be what it can calculate today. It may be what its progress suggests could become possible tomorrow. For decades, researchers have known that quantum mechanics provides a fundamentally different way to process information. The difficulty has been turning that theoretical advantage into a dependable machine. Quantum systems are incredibly sensitive. A classical computer can operate while surrounded by ordinary environmental noise. A quantum processor requires much more controlled conditions. Its superconducting circuits must be maintained at extremely low temperatures, while sophisticated electronics continuously manipulate the quantum states. Even then, errors remain unavoidable. That makes quantum error correction central to the entire field. The concept sounds counterintuitive at first. Instead of using one physical qubit to store information, researchers can distribute quantum information across many physical qubits. If individual components experience errors, the system can detect patterns associated with those errors and correct them without directly destroying the underlying quantum information. The long-term goal is to create logical qubits that are substantially more reliable than the physical qubits used to construct them. Willow's error correction results are important because they indicate that increasing the size of an error-correcting system can actually improve reliability. That is a crucial step toward fault-tolerant quantum computers. Imagine the difference between controlling a handful of fragile instruments and managing an enormous orchestra where every instrument is constantly producing small errors. A useful quantum computer must coordinate all of them while maintaining the information encoded in the overall quantum state. That is the engineering challenge. And solving it could open doors to applications that are difficult to achieve with conventional machines. One major possibility is chemistry. Molecules are themselves quantum systems. Simulating their behavior on classical computers can become extremely demanding as the number of interacting particles increases. A sufficiently powerful quantum computer could potentially model chemical systems more naturally, helping researchers investigate catalysts, materials, batteries, and pharmaceutical compounds. Another possibility is materials science. Scientists could explore how exotic materials behave at the atomic level and search for new properties that are difficult to predict using conventional simulations. Cryptography is another area where quantum computing could have major consequences. Large fault-tolerant quantum computers could eventually threaten some widely used public key cryptographic systems. That is one reason governments, companies, and researchers are already developing post-quantum cryptographic methods designed to remain secure against future quantum attacks. But none of these possibilities mean that quantum computers will make ordinary computers obsolete. Classical processors will remain extremely useful. In many tasks, conventional hardware is faster, cheaper, and more practical. Quantum processors are expected to operate as specialized accelerators for particular classes of problems. The deeper philosophical questions are just as interesting. Quantum mechanics has always challenged our intuition about reality. Particles can behave like waves. Measurements influence what can be known about a system. Entanglement can connect quantum states in ways that have no simple classical equivalent. Different interpretations attempt to explain what the mathematics means. The many worlds interpretation is one possibility, but quantum computing itself does not prove that interpretation correct. Willow cannot be used as evidence that alternate universes have been experimentally accessed. What it does demonstrate is something more concrete. Quantum behavior can be engineered. Phenomena once confined to theoretical discussions can now be manipulated inside carefully constructed machines. That is perhaps the most remarkable transition. Humanity has moved from asking whether quantum mechanics can be harnessed to building processors that depend on it. The journey is still at an early stage. Hundreds of physical qubits are not yet equivalent to hundreds of perfectly reliable logical qubits. Scaling remains extremely difficult. Error rates, control complexity, cooling requirements, and manufacturing challenges all become increasingly important as systems grow. But every improvement in error correction moves the field closer to a machine capable of performing useful calculations at scales that classical computers cannot efficiently reproduce. Willow is therefore not the end of quantum computing. It is another step toward a future in which information itself can be manipulated according to the deepest rules of physics. And perhaps that is the real story behind the quantum revolution. We are not discovering a machine that breaks the laws of physics. We are discovering how to build machines that use those laws in ways our classical intuition never prepared us for.